Let us consider a differential equation. Derivative of y with respect to x equals to some function of x and y. Then this differential equation is going to be separable only when our function f of x comma y, this can be expressed as the product of two other functions g and h, such that g is purely a function of x times h, where h is purely a function of y. In that case, our differential equation will become dy over dx equals to g of x times h of y. Or we can simply rewrite this as dy over h of y equals to gx times dx. Here we can observe that the coefficient of dy, which will be 1 over h of y, is purely a function of y, and the coefficient of dx, which is g of x, is purely a function of x. So this is what we have obtained, is referred to as the separable form of a differential equation. And once we have obtained the separable form, then we'll integrate both sides. So this will be integration dy over h of y equals to integration of gx dx. So that means we will obtain the entire derivative of h of y, which will be uppercase h of y equals to entire derivative of g of x, which will be uppercase g of x, plus some constant of integration which comes out by integrating both the two integral, but we will consider a single constant of integration. Let's call it constant a. Right. So this is going to be the general solution to our differential equation. So this is a general solution. So there is another type of solution also referred to as a particular solution. So particular in the sense, if we are given some sort of conditions, also known as initial conditions, these conditions, if they allow us to obtain the value of this constant a, then what we obtain is referred to as a particular solution. Let's understand this idea with the help of an example. So we have our first problem. We want to determine the general solution to this differential equation dy over dx equals to negative xy. So here, if we look at the function, our function f of x comma y, so this is negative x times y, which can be thought of as a product of two functions g of x and h of y, where you can consider g of x to be equals to negative x and h of y equals to positive y, but the sign is interchangeable. We can also have considered g of x equals to positive x and h of y as negative y. That's totally your choice. So that means we can convert this differential equation into a separable form. So we can rewrite this as dy over y equals to negative x times dx. So this is in the separable form. Once we have obtained our differential equation in the separable form, we are ready to integrate both sides. So this will be integration of dy over y equals to negative integration x dx. The integration of dy over y, so that will be natural log of absolute value of y equals to integration of x, that will be negative x squared over 2 plus some constant of integration, let's call it I. Here, this is referred to as the general solution. However, we can further simplify this so that we obtained the solution in terms of y. So to do that, we have to get rid of this logarithm. We will use the definition that whenever we have natural log of a, and if this is equals to b, then a will be equals to e raised to the power of b. So we are converting the logarithm to exponents. So that means we have here y. So y will be equals to e raised to the power of negative x squared over 2 plus a, which will be equivalent to e raised to the power of negative x squared over 2 e raised to the power of a. So a here is a constant already. So e raised to the power of a, this is also going to be another constant, which we can represent it as equals to c. So that means our general solution will be y equals to e raised to the power of negative x squared over 2 times c. So this is our general solution. Now, to check whether if it is truly the solution of our differential equation, there are several ways. One of the way will be if we take its differentiation of this general solution, then this should give back us the differential equation. And another way to look at it will be if we consider the slope field of this differential equation, then the slope field is going to give us what's the solution of this differential equation is going to look like. So let's try out both of them. So we have y equals to a constant c times e raised to the power of negative x squared over 2. Let's take the derivative on both sides with respect to x. So we have dy over dx equals to c being a constant. This will be multiplied to derivative of e raised to the power of negative x squared over 2, which will be equals to c times the derivative of the exponential function. That's simply the exponential function. And we also have to use the chain rule, so multiply it to the derivative of negative x squared over 2. So this is c. So c times e raised to the power of negative x squared over 2 times, we have negative half multiplied to derivative of x squared, which will be 2x. So the 2 and 2 gets cancelled. We have negative x times this factor c times e raised to the power of negative x squared over 2. This can be replaced with y. So we have obtained our required differential equation. So that means this is indeed the general solution to a given differential equation. We can also try out the slope method. So this is going to be the slope field for the given differential equation, and if we try to predict what's the solution is going to look like, then we can follow the slope line. And this is going to give us the family of curves represented by the given differential equation, and this is the shape of our familiar bell curve, which is e raised to the power of negative x squared. So that means our solution, which we obtained as y equals to c times e raised to the power of negative x squared over 2. This is indeed correct. Okay, let's try out another problem. So here we have an initial value problem. So this is a differential equation whose initial value is given. That means that x equals to 0, the value of y is 1000. And we have to find a solution to this differential equation. So let us begin. Our differential equation is dy over dx equals to 0.02y. What we can do here is we can separate the differentials. This will become dy divided by y equals to 0.02 dx. So this is in the separable form. That means we can integrate both sides. Here 0.02 is a constant, so we have pulled it out of the integration. The integration of dy over y, so that is natural log of y equals to 0.02 times integration of dx, so that's simply x, plus the constant of integration a. And this can be also written as y equals to c times e raised to the power 0.02x, where we have considered c to be equals to e raised to the power of a. Now we will use the initial conditions y0 equals to 1000. So this means that when x equals to 0, this implies y will be equals to 1000. So let's substitute this into our equation. So this will give us 1000 equals to c times e raised to the power of, we have 0.02 multiplied to x. Our x value is 0. That means 1000 equals to c times e raised to the power of 0. E raised to the power of 0 is 1. So that means the value c is 1000. We'll substitute this into this equation such that our general solution will then become y equals to 1000 times e raised to the power 0.02x. So this is the solution to a given initial value problem. Now we'll try to work around this problem more. So we have, let's say this y represents the population and x represents the time. Now, we want to find out, suppose this y, let's say this doubles to become 2y. The question is, how much time does it take for it to double to 2y? So we can use this differential equation and its solution to find out the doubling time. Okay, fine. So let's use this solution. So we have now, in place of y, we have 2y. So 2y will be 1000 times e raised to the power of 0.02 x. So our goal will be to obtain this doubling time. So here y, so y initially is 1000. So when it becomes double, so this will simply becomes 2 times 1000 equals to 1000 times e raised to the power 0.02 x. So the 1000 and 1000 goes away. So we have e raised to the power of 0.02 x equals to 2. Let's take the natural log on both sides. So this will give us 0.02 x equals to natural log of 2. We have x equals to 1 over 0.02 times natural log of 2. And let's plug this into a calculator, and this should give us, this gives us approximately 34.66 units of time. That means it is going to take us, if we consider that x is in, let's say, in hours for this particular instance, then the doubling time will be 34.66 hours. That means in that time, if the initial population was 1000, then it's going to become 2000 in this particular amount of time. So let's go to the next problem. So we need to determine the solution to the initial value problem. This is quite similar to the previous problem except for this negative sign. So this is going to bring a whole lot of change in our problem. So let's consider the differential equation. We have dy over dx equals to negative 0.02y. When we separate the differentials, we have dy over y equals to 0.02 dx. We'll take the integration on both sides. So integration of dy over y, so that will be natural log of y equals to negative 0.02. Integration of dx will be simply x plus the constant of integration a. So y will be equals to c times e raised to the power of negative 0.02x, where our c is e raised to the power of a. Now, we'll apply the initial conditions. y0 equals to 1000. So that means when x equals to 0, y will be 1000. So we'll have 1000 equals to c times e raised to the power of negative 0.02 times 0. So that's simply 0. That means the value of c is 1000. So our solution will be y equals to 1000 times e raised to the power of negative 0.02x. So this is the solution. This is a particular solution to a given initial value problem, and the solution, we have a negative exponential here. So that means it starts off at initial value of 1000. That means when x equals to 0, and then gradually it's going to decay and reach almost 0 as x goes to higher and higher values. In the previous problem, we considered the doubling time. So this time we're going to consider the half time. So half time would mean when our y, which was initially 1000, so that means it becomes half y over 2. How much time would it take? So let's try that out. So for this differential equation, we obtain the solution y equals to, we want to find out the half time. Half time would mean when y becomes y over 2. So we have y over 2 equals to 1000 times e raised to the power of 0.02x. Y initially was 1000, so this will become 1000 over 2 equals to 1000 times e raised to the power of negative 0.02x. So this 1000 and 1000 goes away. So we have e raised to the power of negative 0.02x equals to half. Let's take the natural log on both sides. This will be negative 0.02x equals to natural log of half, and natural log of half is also negative log of 2, such that x will be equals to log of 2 divided by 0.02. Let's obtain this value. So this will be equals to 34.66 units of time, which surprisingly gave us the same result as previous one. But there's a difference. In the previous one, the population doubled in 34.66 units of time, whereas in this particular case, if it initially was y, then in 34.66 units of time, it became half. So this problem could mean anything. Here, y could be some radioactive material which took 34.66 units of time to become half of its initial value. So this is how we can solve differential equation.